Thank you for attending this presentation of Applied Math and Physics in STEM, where we'll explore the real-world applications of math and science by using a process of guided inquiry-based learning. In today's presentation, we'll explore 4 big ideas. This will include a brief exploration of the true nature of STEM education, some recommendations for best practices for STEM education, and these practices will be modeled throughout the presentation, and an in-depth exploration of how we can apply math and physics in an authentic way. And we'll conclude with the idea of developing curriculums that will withstand the test of time. So with that said, let's start with big idea number 1. What is STEM education? So it's widely accepted that STEM stands for science, technology, engineering, and mathematics. It seems that everyone knows what STEM is, but there's a lot of confusion and uncertainty surrounding STEM and all of its derivatives. So let's delve into this a bit more. Now, I think most people are aware of Bloom's taxonomy, but for those of you who don't, Bloom's taxonomy is a classification of the different levels of thinking or cognition, where knowledge is at the bottom, and as we develop our understandings, we can start applying what we know and eventually start synthesizing and evaluating the results of our own thought process. And I think this is an important thing for us to stop and think about. Everyone seems to have knowledge of what STEM is, but very few people understand the true nature of STEM education. And we as educators know that there's a big difference between knowledge and understanding. Now, because of the confusion surrounding STEM education, there's been a number of criticisms that have been made of the framework over the years. Now, while these criticisms are valid, they only identified a problem without understanding what caused the problem in the first place. And these criticisms resulted in a number of STEM derivatives which have only created more confusion for educators and administrators alike. So let's take a look at some of these acronyms. So we have STEM, and we have STEAM, which adds creativity through the arts. But we have STEMS, which recognizes the importance of social science by adding the S at the end of the acronym. STEMA, which adds managerial arts and was first proposed by Harvard University. Next, we have ESTEAM, which recognizes the importance of developing English literacy development. And the idea of including an ESL curriculum into the STEM framework is important for non-English speaking countries so that students can access a wider range of research materials which will help them become more innovative. And this leads us to another derivative known as STREAM, which adds reading or research. And finally, we have STEM with a double M, which was created by Dr. Stephen Meyer and Reverend John Getz, who added the values of Christian missionary to the values of STEM education. And this ties in with the recommendations that the World Economic Forum had, but from a slightly religious standpoint. And it also corresponds to the Chinese interpretation of STEM plus Sijiaoyu, or moral education. So this definition is true to the initial definition that was introduced in 2001 by Judith Ramley, who at the time was the director of the National Science Foundation Education and Human Resource Division. So let's read through this definition together. STEM education is an interdisciplinary approach to learning where rigorous academic concepts are coupled with real-world lessons as students apply science, technology, engineering, and mathematics in context that make connections between school, community, work, and the global enterprise, enabling the development of STEM literacies and with the ability to compete in the new economy. Wow, this definition is very verbose. So I'm going to highlight a few key words here. Interdisciplinary approach, rigorous academic concepts, real-world lessons, apply science, technology, engineering, and mathematics in context to compete in the new economy. So STEM is actually linked to economic goals to help students compete in the new economy. And we can't really forget about this connection because this is really the main driving force at the government level for STEM. But let's try simplifying this definition. STEM solves real-world problems using science, technology, engineering, and mathematics. So this is the simplest definition that I can make to define STEM. However, this perception of STEM education, which I've represented by a red box, is incredibly limited. Therefore, we need to add more depth to our working paradigm. So let's expand the boundaries of our understandings. So if our aim is to solve real-world problems, then the problems that we explore should be authentic. By extension, the solutions to that problem should also be authentic. And finally, the approach should also be cross-curricular. But professionals in the fields of STEM are also addressing real-world needs in our society. And these industry professionals are leading innovation through creative problem solving. So we now have a definition that's much simpler to understand, and it still upholds the ideology of the original definition that we looked at a moment ago. However, there is still one last point that I should emphasize. Although students will often learn numerous skills in STEM, the focus of STEM education is not to develop job skills for a general labor market. So I would like to share this graphic to show you how all of these different concepts are interconnected. from the various subjects that STEM is comprised of, the critical industry sectors that STEM is related to, the educational theory that intersects with STEM education, and the various stages of cognitive development. As you can see, the core subjects, math and science, act as columns supporting everything, and these core subjects are supplemented by interdisciplinary subject areas. So STEM acts as a merging point for the core subjects as we apply rigorous academic concepts and real-world lessons that will help students prepare for the new economy. However, there's so many critical sectors that are represented by STEM. So after we see the merging of these core subjects, we also see STEM branch out into a number of specializations that all fall under the STEM umbrella. This creates an hourglass shape as we take multiple subjects, bring them all together, and then spread out again as we go on to specialize in a specific field of study later on in life. And that brings me to Bloom's taxonomy. As you can see, we always start with knowledge, and as we learn the basics, we start to understand abstract concepts. These concepts could include how to solve an equation or how molecular bonds work, and these are all important concepts to understand if we're going to start applying theories in real-world lessons in a STEM program. So you can see the core subjects really need to precede STEM because we cannot apply math and science before first understanding the basics. Then in STEM we can start applying what we've learned in context to solve real-world problems and go on to analyze the results. And finally, later in life, industry professionals are required to synthesize seemingly unrelated concepts to solve complex problems in the real world. And of course, they'll need to evaluate the effectiveness of those ideas as well. Next, we can look at where we're going to get the greatest impacts in STEM. Since critical thinking, math, and science are all crucial skill sets in STEM education, you'll find that STEM will have the greatest impact when it's taught in the middle and high school levels. And this notion also corresponds well with what we know of Piaget's theory of cognitive development, which indicates that logic and abstraction only starts at age 12 and continues on through adulthood. And that brings us to big idea number 2, where I'd like to briefly talk about best practices for STEM education. So the first thing I want to talk about is inquiry-based learning. Now, inquiry-based learning has its proponents. However, there's also lots of teachers out there that are strongly opposed to this philosophy as well. But I think the biggest issue comes down to the differences between guided and unguided inquiry-based learning. That is, are we as teachers creating authentic learning opportunities for our students that will challenge them to ask questions, while also giving them the support and guidance they need to excel? Or are we leaving them to their own devices and hoping for the best? So I would argue that the opposition that some teachers have towards inquiry-based learning is actually directed towards unguided practices. Now, Joseph Schwab recommends that students practice inquiry in laboratory instruction as it presents opportunities for students to acquire knowledge by asking questions. So inquiry-based learning isn't about letting students do whatever they want and seeing what they come up with. It's about helping our students discover new things by asking questions in a structured setting such as a lab. However, we're not disseminating information through formal explanations, but guiding our students through a process of practical inquiry. And when we fail to provide structure, support, and guidance to our students will typically apply what they already know or what they're currently capable of doing. And as a result, they will seldomly go beyond a rudimentary understanding of the concepts that are related to what they're exploring. This is in part because they won't even know what questions to ask unless we point them in the right direction. Therefore, unguided inquiry-based learning tends to produce projects like this. Here we can see that the students have used popsicle sticks to create an object that resembles the general structure of a crane. However, very few scientific principles have been explored in this example. Alternatively, the students may use a do-it-yourself kit, and while there's nothing wrong with the quality of these products, the students don't really learn much from these resources because they focus on the act of building rather than exploring rigorous academic concepts. And these kinds of resources have been giving STEM education a bad reputation. For instance, Fung criticizes STEM, saying that STEM education is only concerned about the project itself. Therefore, in summary, neither of these examples had students explore scientific concepts beyond the rudimentary function or shape of a crane, and that negates the value of doing the project in the first place. Now in this example, you can see what a project would look like using a guided inquiry-based learning methodology. Now you can see by this example that the students have conducted a much deeper exploration, and the quality of their project is infinitely better. While the video does an excellent job of showing the final product, we don't really see what happened behind the scenes. So for the remainder of this presentation, I'll be using this project to model how math and physics can be applied in an authentic way. But before moving on, I also want to emphasize this point. All teachers are language teachers. We can't just push off aspects of literacy development just because we're teaching STEM. We have our part in helping students develop cognitive academic language proficiency skills to help prepare them for the new economy. And as trends indicates, countries with higher English proficiency are more innovative as they have access to a wider breadth of current research materials from the global community. Therefore, it's imperative that we help our students, especially if we're teaching STEM in an international setting, so that we help develop the literacy skills that our students will need to excel. And to do this, we need to make an effort to reinforce and teach vocabulary skills as well. And so these are all the vocabulary words that I'll be using while modeling this extended project. Now, it's important for me to explain and model how to use these words properly. However, I always go a step further by providing my students with the IPA pronunciation guides for each word. And this really helps our ESL students as it provides them with a resource to sound out the words properly on their own. Therefore, the use of IPA empowers them to become autonomous, self-directed learners. But I also try to reduce how many words I use. For example, I avoid using unnecessary synonyms. And this helps me to use select keywords more often, which helps the students learn through repetition. Moreover, this will help reduce confusion amongst ESL students as well. And finally, I always hide keywords in my lessons to help draw the students' attention to important vocabulary words. Moreover, it's also important to be very clear with any abbreviations that you use, and to be consistent in how you use them. For example, pre-made diagrams can be labeled very differently depending on their source, and these discrepancies can be very confusing for your ESL students. Therefore, it's best to ensure consistency throughout your lessons. As such, I'll be using these exact abbreviations in today's presentation. And that brings us to big idea number 3, which is the main focus of this presentation. How do we apply math and physics in an authentic way within the context of STEM education? And to do this, I'll be modeling a single project, which is the development and testing of a tower crane. Now, I've already shown you examples of what the end product of both guided and unguided inquiry-based learning will look like. However, we haven't seen what we can do as teachers to guide and support our students, which is important if we want to encourage an authentic process of inquiry that will promote the development of rigorous academic skills. So the first thing we need to do when understanding a crane is to learn the basics. Essentially, what we want to do is to activate prior knowledge, or draw on dormant observations of the real world, or potentially introduce new concepts for the first time. So at this stage, we'll be introducing students to the idea of trusses, what they are, how they're made, and how they're used to create a more complex structure. And this is a transferable concept that gets used in bridges, buildings, and even in spacecrafts. So I should say that the project within STEM are only a means to an end. Things shouldn't really be about the project itself, but about the core concepts that the projects represent. And these concepts should really be big transferable ideas that will transcend the project, but more importantly, that will transcend time. So this is the challenge that I would give the students: to design, build, and test the strongest crane possible. And this one project is going to cover aspects of structural engineering, mechanical systems, and electronics. So there's a lot of things that a project like this can cover if we help guide our students through a process of guided inquiry-based learning. And this will give them an authentic learning opportunity to explore the application of math and science in context. Now, cranes are designed using trusses which support the load, and these loads will result in different forces that act upon the structure of the crane. And just as an aside, you can see how I've highlighted the keywords, and I've also added visuals such as symbols to help my ESL students identify the big ideas. So moving on, if we take a look at our standard truss, as we apply a load to the middle of the structure, we're able to see the force which is exerted by the load disfigures the structure. And different parts of the structure will experience different types of forces, as parts of the structure are compressed, while others are being ripped apart by forces of tension. Now, trusses are constructed using triangular units, which are known as nodes, and this creates a long planar support that's known as a truss. And these planar supports are then used to create a three-dimensional frame. Now there's lots of different types of trusses such as the Bailey, parallel chord, Parker, and the Warren truss design, just to name a few. And this is where the student's inquiry really comes into play. As we've seen, as we've created a scenario for authentic inquiry-based learning where we are guiding our students to explore new concepts. Therefore, the student's challenge is to design the best crane possible using standard trusses. However, they'll need to ask themselves which truss will produce the best results and why. For instance, the Bailey truss is incredibly strong. However, it's very heavy, so the crane is going to have to support extra weight. And it's also very difficult to assemble a Bailey's truss as well. So we have various trade-offs which our students are going to need to consider. Therefore, your students will need to think about which design is going to be the strongest, the lightest, and the cheapest. And then they'll also need to think about how they balance these factors to achieve the ideal strength to weight ratio while keeping costs down, which is essentially the big idea behind a feasibility study, which the students would learn in an economics class. Therefore, as the students are designing their crane, they'll want to think about what type of truss they'll use to create the mast. Why would they select this kind of truss? Will the truss make their crane stronger? And are they capable of building and testing their own design? Students will also need to think about how they'll design the jib as well. And will they modify the truss design here? For instance, they may decide to taper the jib at one end to reduce the weight, or they might add a pivot point, because a lot of cranes do have a pivoting point. Regardless of the choice of the students' choices that the students choose to explore, they'll need to ask themselves the following questions. Will this make my crane better or worse? And is this a design within my ability to make? Now, this pivoting truss idea is really cool. However, it's going to be too difficult for your students to attempt. But here we have this idea of providing the necessary information for your students so that they can make informed decisions to help guide their process of inquiry. And differentiation is inherently built into this methodology, as students will be able to take on challenges that are suitable for themselves. So the first thing students will need to do is to design their own crane. Now at this point, they shouldn't be concerned about things like scale or technical requirements, because we're going to modify these designs later on. So essentially what we're going to do is to continually throw our students curveballs as we guide them through a process of inquiry-based learning. As such, every time the students think that they're done the project, we're going to say, hey, did you think about this yet? And that's going to force them to go back and modify their designs. And this is exactly what engineers are required to do when working on large projects in the real world. At this point, students will have a rough draft. And this really is just focusing on the overall design and what type of trusses they're planning on using. However, we haven't focused on any other requirements yet. And that brings us to pad size. Now this is where we'll determine how large the base of the crane needs to be in order for it to be stable. And this will require us to consider different variables and how they interact with one another. So the load will produce a downward force which can either be distributed across a large area or focused on a singular point. And this brings us to the idea of point load and distributed loads. As we can see, point load acts upon a single point, whereas distributed load applies the same amount of force over a greater area. And this results in different stress factors in a standard object. As we can see, the distributed load applies the force equally across the entire object, which reduces stress. However, the point load focuses that force on a singular point, which creates a lot of pressure or stress on the object. And this results in the deformation of the object. And as we can see in the second diagram without the pads, the point load compresses the midpoint, which can cause the sides of the objects to flex outward to relieve the stress. And eventually this could result in catastrophic failure as the support columns collapse due to structural stress. Now you might ask, why is this important? So this is a picture that I took when I was still working as a photojournalist. And this one photo really illustrates the need for understanding math and physics in this kind of project. So here we have a crane where the operator did not properly calculate the safe operational limits of the crane, and this resulted in the crane toppling over and causing a significant amount of damage. Luckily, nobody was injured. However, things could have been much worse. And this brings me to a comment made by the World Economic Forum about STEM education, indicating that we should also expand the scope of STEM education to ensure that students learn to evaluate and respond to the social, economic, and political consequences of their work. So we should also be looking at the impacts of what we do and why we do it. And if we look at this example, we can see that these businesses are forced to close, which has an adverse effect on their employees, but also on their customers as well. We also have structural damage to these buildings and the time and money that it will take to repair these damages. So there's huge social and economic impacts here, and that's part of what we should be looking at in STEM education. And that brings us why it's important to calculate pad size. Furthermore, you probably never even thought about this issue until I gave you this example. And this really illustrates the difference between guided and unguided inquiry-based learning. So the first thing we need to do is to determine the point load that is exerted by the crane. To do this, we'll add up the weight of the crane's tower, jib, and counterweight. So in this standard crane example, we have a total mass of 125 tons. Next, we need to determine any irregular loads. So in this example, we have irregular loads that account for an additional 13 tons. With our point load and irregular loads known, we're now able to determine the amount of pressure that will be exerted by the crane on the ground beneath it. We use the equation point load multiplied by a constant of 0.75 plus irregular loads, and in our working example, we get a ground pressure of almost 107 tons. After that, we need to determine the ground bearing pressure. Now, these values are based on constants that are provided in a standard lookup table. However, in this example, I'm going to use the value for soft clays, which is equal to 75 kilonewtons per square meter. To determine our minimum pad size, we then divide ground pressure by ground bearing pressure. Once we substitute our values into the equation, we're left with a minimum acceptable pad size of approximately 14 square meters. Now we need to determine the dimensions of our pad, and the method that we use will be slightly different depending on whether we plan on using either a circular or square pad. So at this point, we simply rewrite the equation and substitute the known values. And finally, standard operating procedures dictates that we round all values up for good measure. After that, we determine our outrigger point load, which is determined by taking our ground pressure and dividing that by our final pad size, which is then compared to the ground bearing pressure in a final safety check. Therefore, as long as the outrigger point load is less than the ground bearing pressure, the crane can be operated safely. And all of this comes back to the recommendations that were made by Joseph Schwab, which indicated that students should acquire knowledge by asking questions, exercise observation skills and deductive reasoning, and practice inquiry through laboratory instruction, while also addressing concerns that Fung had when indicating that STEM education is only concerned about the project itself, while it's directing students toward evaluating and responding to the social and economic consequences of their work, as indicated by the World Economic Forum. And this isn't something that would be naturally intuitive if we left our students to their own devices. Therefore, we should be able to see the benefits that guided inquiry-based learning has at this point. And it's important to remember that this approach differs greatly from the front-loading approach to education that we typically see in academic subjects. With guided inquiry-based learning, we use what's called a just-in-time approach, which is where we introduce a model theory when it's most relevant. And this will help guide and shape the nature of our students' inquiry by encouraging them to ask the right type of questions at the right time. So now that we've introduced some new concepts and properly modeled the application of this theory, we can give the students extension activities such as ask them to calculate the pad size for their crane if it was to be placed on either gravel or clay. Then with this information in hand, students will be able to evaluate their own crane designs. And all of this is to help guide the students towards asking themselves the following questions. Do I have a viable crane design? Is my crane design meeting all of the necessary safety requirements? And if not, what can I do to improve the design of my crane? And this is our job as STEM teachers, to help guide our students through a process of inquiry, so that they will develop a deeper understanding of how the math and science is used to solve real-world problems. So at this point, our students will have a generic crane design, and we have also introduced them to a number of equations that will place math into a real-world context. Now we're going to have the students apply that math so that they can effectively redesign their crane. To do this, they'll need to determine the acceptable pad size for a crane that would be used in the real world, and then use those calculations to determine the optimal size and proportion of their model crane, which needs to be built at scale. So at this point, I would give the students a new design template and a number of requirements for the projects, which will help the student and this will really help keep the students on task. These guidelines are really helpful to give your students because you'll always have students that will make computational errors. Therefore, by providing these requirements up front, students can quickly self-assess their work and catch their own errors early on in the process. Now, the students are also going to have to keep 3 different scales in mind when working on the project. The actual size of a real crane, which will be at a scale of 1 to 1, the size of their prototype or model, which will be at a scale of 1 to 100, and the size of their drawing or schematic, which will be at a scale of 1 to 500. I should also mention that these are not standard engineering scales. Instead, I've selected scales that will greatly simplify the math for my students, and this will help them focus on the big ideas and not get tied up with trivial details that are better left for another time. So at this point, the students should be able to determine the pad size of a real crane and then use that information to ascertain the ideal measurements for use in their model crane. So let's say we found the optimal pad size was 6 by 6 meters. We can then use that information to effectively redesign the schematic for our model crane. For example, with a scale of 1 to 100, the base of our crane would be 6 centimeters wide based on the previous calculations. Moreover, with a 6 centimeter dimension for our nodes, we can connect 16 nodes to create a mast that's 96 centimeters tall. And all of these dimensions are within the specified project requirements. So the real-world application of math is really the most important aspect of the project at this point. Then, with all the calculations completed and a new design schematic made, students can then move on to building the crane as you see in these project exemplars. So once your students have finished building their crane, they will likely think that they're done the project, which is the case with the unguided inquiry-based learning methodology that we saw earlier. However, the reality of the fact is that your students have just started this project. So a crane's main purpose is to create a mechanical advantage, and it does this through a combination of several simple machines such as levers and pulleys. Therefore, we still need to determine how to calculate the mechanical advantage of these systems. Moreover, we still need to design and build a pulley system for our crane as well. So again, we need to think about how we strategically introduce topics to help guide and shape the nature of our students' inquiry. As such, the next idea we need our students to think about is how levers are used to create a mechanical advantage. So lever can change where a force is applied, change the distance or speed that a force is applied, change the direction of the applied force, or can increase the magnitude of the force. Furthermore, the relationship between the fulcrum, the input force, and the output force are important concepts for students to understand. Now, there are 3 different classes of levers, and they each work in a different way. An example of a first-class lever would include a crowbar, whereas an example of a class 2 lever would include a wheelbarrow, and finally, a shovel is a great example of a third-class lever. Now, I've gone through this incredibly fast. However, my intention is not to teach you these concepts, but to provide you with a quick overview of what an authentic application of theory would look like in context. So before moving on, do you know what type of lever a crane uses? Well, a crane uses a class 1 lever. Now we can use the following equation to determine the mechanical advantage of the system. In this example, we take the 12 centimeter distance of the effort arm and divide that by the 4 centimeter distance of the resistance arm. And this will give us a mechanical advantage of 3. As a result, the small 400-gram weight is able to counterbalance a weight 3 times its size. However, a slightly more sophisticated version of this formula is needed for our calculations. So using the equation m1 times a equals m2 times b, we're able to calculate the maximum safe load that can be lifted at a crane at any point along its jib. So the first thing we need to do is plug in our values. Then we isolate our unknown variable, find the product of the numerator, and then simplify, which will leave us with a maximum load of 5 tons at position 1. However, the hook block is equal to 0.5 tons. Therefore, the actual weight of the load is equal to 4.5 tons at position 1. Then we would repeat the process for the remaining positions, and as we can see, the maximum weight at position 2 is only 2 tons. Now the math that I've shown you is not overly complex. However, the concept says these equations represent R. For instance, all of these equations have been taken from a 68-page UK Ministry of Health and Safety guidebook for safety auditors. And again, it would be highly unlikely for our students to take the time to do this on their own. However, by modeling and guiding our students, the process of inquiry-based learning becomes far more holistic. As our students exploration becomes far more rigorous than it would have been otherwise. And that brings me to another big idea, which is making connections between various subject disciplines. To illustrate this idea, I've made a series of graphics. So a designer is primarily concerned with researching their client's needs and creating a design. However, an engineer is more concerned with the math that's needed to make the designs a reality. And finally, the mathematician. Now, they don't really care about the design. They only really care about representing the world through numbers and variables to simplify the world to orderly equations that can be solved. And although this final representation looks incredibly different from the first diagram, it still represents the same problem. So I want to use this example to illustrate how we can take the math even further. Now, the method that I showed you earlier would be suitable if you were to do this project with an intermediate grade level. Therefore, I'm going to model how we can place what students would be learning in a senior physics class into a suitable context. Well, the equation m1 times a equals m2 times b would reinforce what the students would have learned in an intermediate science program. The equation for angular momentum and torque would allow us to solve the same problem using concepts from a senior level physics curriculum. So here's a question that I've taken directly from a physics textbook, and we can see how this question relates to our crane project. Now, this is not the actual diagram that was shown in the textbook. I actually made a few modifications to the diagram to place the theory into a suitable context. So now that we understand what we're trying to do, let's look at the steps necessary to solve this problem. So the first thing we need to do is simplify the diagram if it hasn't been done already. And this is actually what the diagram looked like in the textbook example, a pure mathematical representation of the problem with no context. And if you look closely enough, you'll notice that the information between these two diagrams is identical. The next thing we need to do is write the equation that represents the system. And because we can assume that this system is in a state of static equilibrium, the summation of the cross products must be equal to 0. And that's how we arrived at this equation. Next, we'll need to determine the cross products, and if you teach physics, you'll probably be aware of the right-hand rule. But essentially, P1 will have an outward cross product, whereas P2 will have an inward cross product. And these are notated using the symbols and the variable notations that are shown on the screen. At this point, we'll need to determine the torque that each variable in the system will produce. So if we work our way through the process, we can simplify P1 to dmg, and what that essentially means is that d indicates the position of the mass along the jib, and that is multiplied by g, which is the force of gravity. And we'll do the same for P2, and this will give us the final solution of xmg. And finally, we'll do the same for P, and this will give us 2 dmg. Next, we'll plot all of the weights in 3 dimensions, which will give us a graph that should look like this. And based on the graph, we should be able to see that the net force will equal 0. Therefore, we can substitute the values we derived from step 4 into the equation, and this will give us the equation dmg minus xmg minus 2 dmg equals 0. Then we can substitute the values that was given for m in the original problem. Now, the force of gravity is common to all variables, therefore we can divide it out and all of the variables by g and cancel it out. And this will leave us with the following simplified equation. We'll then need to simplify the equation even further, and this will give us a final value for x. Next, if we assume that x is equal to 0, we can simplify and find the value for m. And finally, we substitute all of our values, and we'll find that large m is equal to small m when the moving mass is equal to negative d. At this point, most people's heads are probably spinning. But this example was really meant to demonstrate how abstract concepts can be given new meaning through the authentic application of theory in STEM education. Therefore, at this point, our students should be able to calculate the maximum safe weight, convert measurements between actual and model size of their cranes for testing, and that would imply that students can calculate the point load and irregular loads of a real crane, and then use that information to determine how much weight our model crane should be able to support. And based on this information, we should all be able to conclude that the mast of our model crane should be able to support 50 kilograms, while the jib should be able to support 1 kilogram at its furthest point. And this will give us suitable parameters for testing and evaluating our model crane. At this point, students will have completed the overall structure of the cranes. So now students will need to design a pulley system. Moreover, the system needs to be able to create a noticeable mechanical advantage. And this is because a typical 5-volt DC motor will not be able to handle a vertical lift for a 500-gram load on its own. And at scale, our ideal target weight is going to be 1 kilogram. Therefore, we're not finished with the laws of physics just yet. So we've covered a lot of information so far, so let's do a quick review. A crane is made of 2 parts, the mast and a jib, and mechanical systems are used to raise or lower the load using a pulley system. Therefore, the next thing your students will need to do is to design a pulley system for their cranes, and this will require them to retrofit their original designs, which will present them with a series of unique design challenges to overcome. Now, a pulley is one of 6 classical machines and consists of a rope that's partially wrapped around a wheel to lift a load. And this brings me to Newton's 3 laws of motions. First, an object will remain at rest unless acted upon. An applied force will cause an object to accelerate. And finally, for every action, there's an opposite and equal reaction. However, we're interested in Newton's 2nd law, force equals mass times acceleration. Now, without a pulley, an object will experience 2 different forces. These are the effort that's needed to lift the object and the force load, which is the force created as a result of gravity. However, with a single fixed pulley, we can change the direction of force effort, which makes it possible to pull down on a rope to lift an object. And with a movable pulley, we can cut the amount of effort needed to lift an object in half. Therefore, with a simple pulley system, engineers can change the direction of the applied force, or they can create a mechanical advantage that would make lifting the load easier. And that brings us to designing a pulley system. So the combination of multiple simple machines such as a pulley and lever create a complex machine. And that's our goal, to guide the students through a process of creating complex machines which is capable of producing a mechanical advantage. So now that we understand force effort and force load, the students will need to understand the difference between simple and compound pulley systems so that they can start asking the following types of questions. How much mechanical advantage must my pulley system produce to lift the desired load? What type of pulley system will produce the best results? How can I go about retrofitting my crane to accommodate the addition of this new pulley system? And do I need to modify my idea to make my designs work? And this type of application of theory is created by this line of question, which has been created as a direct result of the guided inquiry-based process. Now, the first type of pulley system that students might want to explore for their crane is a simple pulley system. With a simple pulley system, 2 fixed and 2 movable pulleys are used to create a mechanical advantage of 4-to-1. And additional pulleys will increase the mechanical advantage to a ratio of 6-to-1. And the pattern will continue, which gives us the formula MA, mechanical advantage equals 2 times N, where N is the number of movable pulleys in the system. The second type of pulley system is a compound system. Pulleys are stacked in a vertical configuration in a compound system. Now, this may not be particularly evident from the first example. However, the benefits of stacking pulleys will become increasingly more evident in the following 2 examples. In this example, there are only 2 movable pulleys. However, we're able to create a mechanical advantage of 4-to-1. And finally, in this example, we've created a mechanical advantage of 8-to-1. Therefore, the resulting pattern is represented by an exponential equation where 2 is raised to the power of n. And finally, compound pulley systems can be simplified by creating what's known as a pulley block. And you see pulley blocks in use all the time at the gym, as most weight machines utilize this design to improve efficiency and reliability. So here you can see how multiple pulleys can be assembled to create a compact pulley block. And again, as this is representative of a compound system, the pattern is exponential. So we use the equation MA equals 2 to the power of n, where n is the number of movable pulleys in the system. So with all this theory at the student's disposal, it's now time for them to start designing a pulley system for their crane. And this would be a good time for them to incorporate technology in an authentic way. For instance, in these examples, the students used computer-aided design software to create parts that could be manufactured on a 3D printer. They then used these parts to create the pulley system of their crane. And you might have noticed some of these parts from the video that I showed you at the start of this presentation. While understanding how to create mechanical advantage using either simple or compound pulley systems is critical to this project, you may also want to take the scenario a little bit further. This will allow you to continue to place scientific theories into a real-world context for your students. And in doing so, you'll continue to explore rigorous academic concepts that will help prepare your students for the real world. So we often use an Atwood machine when teaching about forces in science, and this simple contraption uses two masses. So in this example, both masses are equal, therefore the system will be in a state of neutral equilibrium. However, if the two masses are not equal, then both objects will experience an acceleration in opposite directions. In this example, the total mass is accelerated by a force that's equal to the difference in the two masses. Therefore, the net force of the two masses is the difference between the two weights. However, the two masses will have the same numerical acceleration and can therefore be treated as one system when applying Newton's second law. And that brings us back to the equation force equals mass times acceleration. So what happens if we remove the second mass altogether? How much force would be needed to lift the first mass? And this will result in, and to do this, we need to use the equation force equals mass times acceleration. So let's assume that m1 has a mass of 7.5 kilograms and the force of gravity is 9.8 meters per second squared. We'll substitute our known values into our equation and then we'll solve the system. And this gives us the necessary force required to lift the object. Therefore, at this point, students should be able to complete the following calculations. Apply different theories to make calculations relevant to the design of their cranes, including how much force the winch and pulley system must exert to lift the load off the ground. Moreover, students could also explore some of the worst case scenarios pertaining to safety and risk management. And this would satisfy the mandates from the World Economic Forum, which indicated that STEM education should ensure that students learn how to respond to the social and economic impacts of their work. And they can also apply theories that they covered so far. For instance, they could calculate how much time the workers would have to reach a minimum safe distance in the event of a catastrophic failure. So we've covered a lot in this one project already. However, we've only covered the math and science behind the development of a crane, and we haven't even looked at the engineering practices that would be necessary to design and build the electrical systems for our crane. And these concepts are highly transferable as they lay the foundation for mechanical and robotic systems alike. So the importance of this last component cannot be understated. So in order for our students to create a comprehensive control system, they'll need to create a circuit that convert the power from an electric generator, and then make a circuit that can stabilize the irregular output from a generator, so that we can use a DC motor control circuit to control the crane's winch, and a timing signal generator to control the crane's safety light system. So that's a pretty comprehensive list, but this is an example of what it will look like once everything is all said and done. So the first circuit needs to change an alternating current from an electric generator to a direct current, which can be used by our crane's motor and winch system. Now, I'm not going to spend a lot of time explaining how or why this circuit works, but for reference, this concept is covered in depth in the electromagnetism unit of the IGCSE physics curriculum. Now, we can use a half-wave rectifier to eliminate the negative duty cycle. However, this doesn't provide us with a stable output. Therefore, we can use a full-wave rectifier to invert the negative duty cycle. However, a power stabilizer is still needed to provide us with a stable power output. And this is what a full-wave rectifier and a 5-volt power stabilizer would look like in practice. Now, if you're not sure how a full-wave rectifier works, don't worry, because we're going to watch a simulation of this circuit together. So right now you can see the flow of electrons flowing through the circuit, and we can see the values entering and exiting the capacitor changing rapidly. And this is because the capacitor is charging and discharging as the potential difference in the circuit changes. Therefore, when the power cycle is high, the capacitor will start charging and storing power, and then when the power cycle is low, the capacitor will start discharging that power to the rest of the circuit. Now, if you're interested in learning more about these ideas, then you may be interested in watching this webinar. You might be interested in watching this related webinar. Next, we need to create a DC motor control circuit. Now, the simplest design uses a series of switches to control the direction in which electrons flow through a DC motor, and this will allow us to control which direction the motor will turn. Now, this creates a circuit that looks like a capital H. Therefore, these circuits are commonly referred to as an H-bridge. Now, there are numerous H-bridge designs, and these designs range significantly in their sophistication. For instance, basic H-bridge designs can be created using simple switches, and these rudimentary designs allow an operator to change the direction of that the motor turns. However, more advanced designs such as the diode-based H-bridge designs, which are shown to the right, can be controlled using a digital microcontroller. Moreover, various H-bridge designs will provide different levels of functionality. While some DC motor control circuits only provide two states, i.e. forwards and backwards, other circuits designs will also provide a neutral state as well. And here's a short animation that shows how a diode-based H-bridge operates. You can see the flow of electrons changing direction in the circuit when the toggle switch is changed. And you can even have your students create these kinds of computer simulations for themselves using inexpensive CAD programs. For instance, this simulation has been created using iCircuit. However, you could also use circuitlab.com to do this kind of activity as well. And there's so many different ways that you can design an H-bridge, and each method will have its own advantages and disadvantages. Therefore, I like to have every student and group build their own. Afterwards, they'll do a comparative analysis of all their circuits and select the best design for their cranes. Moreover, each student can select a design that's suitably challenging for themselves, which means that differentiation is inherently built into this kind of activity. Furthermore, we're still requiring all of our students to engage with the same learning outcomes, and that's what we really want to see from our differentiation methods. And finally, the last circuit that's needed is a timing signal generator, and this will be used to control the safety light systems of our model crane. Now, one of the best ways to build this circuit is to use a 555 timer. Designed in 1971 by Hans Kemzine, the 555 timer is one of the most vastly and versatile and widely used integrated circuits ever made, with over 1 billion units being sold annually as of 2017. Now, the 555 timer can be used in one of 4 configurations. However, Mode 1 A-stable is suitable for our needs as it will create a regular pulse that will cause our LED lights to flash. Furthermore, numerous formulas are used to calculate the necessary variables. So here we can see how the circuit would look like. And there's a lot of things happening in the circuit as illustrated by this graph. But the concepts are not hard to grasp if we properly model the theory before asking our students to apply it. So here you can see the calculations that the students used to determine what components they needed to build their circuit, I should say, and these choices would have a direct effect on the rate in which the safety lights would flash. Moreover, there's also standard regulations about the placement of the safety lights that the students should take into consideration as well. So at this point, we've guided our students through a comprehensive process of inquiry-based learning. In this process, they would have developed a working knowledge of a number of different control systems and how these systems interconnect with one another. These systems would include a full wave rectifier, power stabilizer circuit, DC motor control circuit, and timing signal generator. Moreover, students should have built and tested all of these circuits as well, and completed additional tasks to install and make use of these circuits. At this point, your students have a fully functional crane design. Therefore, they should be ready to start conducting a series of tests, and these tests should help them evaluate the effectiveness of their crane's design. However, they should be aware of operational limits that would prohibit the use of their crane in a real-world setting. So there's still more teachable opportunities left in this project. So this formula will take environmental factors such as wind speed and its effect on the load into consideration. Using standard wind resistance coefficients, an operator can determine at what point it will no longer be safe for the crane to be operated. The first thing an operator will need to do is evaluate the shape of the object that's going to be lifted. From there, they'll need to properly sling the load. Now, there are government regulations as to the number of slings, the minimum and maximum angles of the slings, and how the slings are attached to the load. Moreover, there is additional formulas to calculate the tension of each sling, and these values are then compared against the tensile strength of the cable. However, I'm going to skip over sling loads and go straight into wind coefficients. In our first example, we have a relatively simple shape, so we can use the wind coefficient for a cube. Now, the first step is to write the full equation and determine what our variables are. Next, we'll substitute all the values into the equation. Then solve the equation, and we should always show every step in the process for good measure. And finally, state your answers using the appropriate units. In this example, the maximum wind speed was equal to 6 meters per second. And that brings us to big idea number 4, which is looking at developing a curriculum that can transcend the test of time. Now, cranes are not a new invention by any stretch of the imagination. From the Roman Colosseums to medieval castles, Levers, pulleys, and complex machines like the crane have always been at the heart of innovation. Moreover, Renaissance science has really advanced our understanding of these simple machines. And even to this day, recreations of these ancient devices remain an academic curiosity for researchers, as you can see by this medieval crane in Prague outside of an old cathedral. But fast forward to modern day, and we can see the importance that cranes have to our society. And this might be evident, and it might be evident that the use of cranes is actually more important today than it was 1,000 years ago. Yet the underlying principles have remained the same. Therefore, I could easily go back in time 30 years and teach the same project, and it would be completely relevant, and doable for that matter, as this project wasn't defined by the use of technology. Moreover, I can say with confidence that this project would be equally as relevant in 30 years from now as it is today. And in all honesty, this project will continue to be relevant until such a point that we can redefine the laws of physics with a breakthrough discovery that would be considered science fiction by today's standards. Therefore, in summary, great curriculum focuses on ideas and concepts that can transcend the test of time and should not be driven by new technologies or fads. Yes, STEM will make use of technology. However, the use of technology must support the desired learning outcomes in an authentic way. We should not let the use of technology become the driving force in the development of our curriculum. Otherwise, we'll likely make short-sighted decisions that will lead to unsustainable educational models. Now, if you found this webinar enlightening, you might want to consider attending any of the other webinars that are related to the development of a high-quality STEM program. All of these presentations are equally as informative as this one, and will provide you with evidence-based examples and projects modeling that will help you design your own STEM programs that will prepare your students for the new global economy. So that brings us to the end of this presentation. In closing, I'd like to thank you for attending this presentation of Applied Math and Physics in STEM. Moreover, I hope you found this presentation informative, and I implore you to consider attending our future webinars as well. Alright, so that's practice run number 3, currently at 52 minutes. I was talking much faster than I normally do, so that is good for a 1-hour run. There's still a few things that need to be fixed, though.